Hello guys, been a while, but yeah, back with another video, and today is gonna be a interesting one because normally we do either analog or either digital kind of circuits, but today I'm gonna try and do a comparison and do both of them in a single video. So as you can see on the screen, we're going to be doing the motor control of this standard servo. It's a very common, all these kits they have them generally. The SG90, it's a small servo motor, a micro one, so very low power, but yeah, it can definitely handle a bit of torque and all of that. So we're going to be controlling this is the shaft here, so we're going to be controlling its movement. So basically how this works is, this is not your standard DC motor, it's a servo motor, so it works on PWM. It unlike your standard PMDC motors. So this is the data sheet, and all of these things are there. It works on 5 volts. So yeah, it's generally designed for microcontrollers. So yeah, you need to give the PWM signal, and what the PWM looks like is, if I can just go down here. So yeah, there are 3 pins on this: the PWM pin, and 2 power pins. So basically it needs a 50 hertz PWM, so the frequency should be constant of 50 hertz, but the thing what decides the, where it is pointing, the direction, it depends on the duty cycle of the, basically the on time of the PWM wave. And we can see that to control the two extreme directions, and between that we need to vary the duty cycle between 1 and 2 millisecond. So this is what this graph says, between 1 and 2. But if you just go up a little bit, this is how it looks, by the way. If you go up a little bit, then on the second page it also does say here that pulse width between this and this, and I tested both of them, and but if you try and vary it between 1 and 2 millisecond, you won't get the entire 0 to 180-degree rotation, and this is a 180-degree rotation servo. So if you want the entire range, then this is the correct one. You need to vary it between 500 and 2400 roughly. So that's what we're going to be writing the code for. So the first thing what we're going to be showing is the digital, or the, microcontroller implementation of it. So I have the board here, the one which I've used many times, the MSP, TI's MSP. So yeah, based on the G2553, which is a nice low power microcontroller. And since we are only going to be dealing with outputting a single PWM wave, and of course since we want to vary the direction, I'm going to be using the same encoder as last time, the rotary encoder. So we just need a single, to a timer to, read these pulses, since this outputs pulses. So we don't really need to pull out the STM for this, the MSP should be good enough. So I'll go into the code here, and most of the code is just for, reading what the encoder's state is and all of that. So I won't really go into that. You can check the encoder's data sheet, and it gives a nice guide on how you can build your own code. And this is a interrupt based code, there is no polling here, so try and keep it as efficient as possible, and keep the CPU involvement less. So what we are basically going to do is keep checking what the current state of the encoder is, and the only thing which is different from the encoder code over here is this, the PWM timer. I've set it up to same up mode, and since it's only 50 hertz, we can divide the clock. It's running at 12 megahertz if I'm not wrong. If I just go into main here, I can see, yeah, the DCO is set to 12 megahertz, so we can really divide that down. We don't really need so much, so I've divided by 2 here, that means I've divided by 4, so it's basically 3 megahertz. And what we get by that is, since this is a 16-bit microcontroller, the registers are basically 16 bits, so the maximum they can hold is 65535 2 power 16. So if you want to try and extract the maximum precision from the registers and resolution PWM of it, then you can try and go as close to 65535 as possible. So since I divided it down to 3, my 50 hertz period comes down to 60,000, which gives us really good resolution. And to to get the mappings, basically you need to use the linear mapping formula. So basically one rotation of your encoder, since this encoder does have tactile feedback, when you do a slight turn you can feel a click which counts as one turn, so you can map what that one turn is. So I think I've given 10% duty change as the mapping. So these are, and I've created a lookup table for that, since we don't really need to calculate that at runtime. The MSP is not that good with multiplications. It doesn't really have a hardware multiplier. So lookup table is good. You can just store it, and if you even say const here, since I've given the const keyword, it will store it in the ROM. So even the RAM overhead will get reduced. So I've mapped what each turn of the encoder means. So basically, in the start, the encoder will be mapped to 0, and if you turn clockwise, then it will increase, and accordingly your timer capture compare register value increases, and in turn your the duty increases. So, and if you decrease it, same thing, it will reduce. And one main thing is you need to add protection over here. If somebody tries and turns the encoder beyond the maximum limit, you need to make sure that it still gets limited to its maximum value. It shouldn't go out of bounds, otherwise some garbage value can creep in. So take care of that. And same for the minimum. If you try and go below, somebody tries and reduces it too much counterclockwise, then it can try and the position will go below 0, and we don't want that. So yeah, just take care of that in the if, and just pass that value to the capture compare register. So the code is not too much to go into. That's it most. And setting up of the pins is mostly you need to set up 2 pins for the encoder itself, and 1 pin for the PWM, which are going to be used to control the servo, and the rest is just one interrupt to keep checking sampling time. So I think I've given a 1 millisecond overflow, so after that it checks the state of the encoder, which should be enough. And yeah, now that this is done, let's go into the hardware. So yeah, now let's get into the hardware, and just a small breadboard setup here, nothing much, just to categorize the wires. I didn't want to have them in the air, so we have a small breadboard here, and the encoder, as I said, and it's wired up to the microcontroller to the said pins what I showed. And the yellow wire here is what is carrying the PWM, and just a 1k current limiting resistor before we give it to the servo motor, which is taped over here. Since my one hand is holding the camera, I can't hold the servo too, so I'll use it one hand to move the encoder. And we have connected it over here. And the servo, another thing which I do need to mention, I think I missed that, is even though the microcontroller does have 5 volt and 3.3 volt pins, and this servo does run on 5 volts, since this draws sudden bursts of current, and they'll easily be in at least the 100 to 200 milliampere range. Of course the microcontroller can't source so much current, so the maximum safe is generally we try and keep it below 10 milliampere. So definitely this cannot source so much current, so you do need a power supply of some sort. So I have just connected a small my bench supply here, and it's set to 5 volts. And since I showed there in the data sheet, if I just go back there for a second, you can see that one pin is PWM, right, and one is the power supply. So you do need to make the power supply and the microcontroller's ground common, so that it registers it. Otherwise it will keep searching for the PWM, but since it's not level shifted, it won't understand. So common the grounds over there, and rest should be fine, nothing much. And just to show you the wave on the oscilloscope, currently since the encoder I haven't touched it yet, it's in the default position, which is minimum, and you can see here it's at 515 microsecond. And as I said, we should vary it between 500 and 2500 for the maximum 0 to 180 degree rotation. So you can see currently it is at 500 microsecond. And now I'll just rotate it once, and first I'll show you how the PWM wave itself varies, then I'll show you the motor. So yeah, I have kept the encoder here, and I'll just show you how the PWM varies first. So I'm going to turn it to the right now. You can see it's increasing in increments of roughly 100 microsecond, and that's what I mapped the lookup table to. So yeah, now we've reached around 1.2 milliseconds. So let's go back to and we can go even maximum. Let's go to the maximum one what it's mapped to. So click, and maximum what it's mapped to is 2.5. So you can see I am turning it further to the right, but it won't go beyond this because we did add that safe condition over there in the if. So maximum is 2.5, and frequency remains constant 50 hertz. So let's go back to the minimum position now, and so yeah, now we're back to the minimum position, and now I'll show you the servo. So we have the encoder here and the servo, and you'll see how it moves now. So now I'll just turn this to the right again, and you can see it's little. I haven't, even though I used the entire 60,000 resolution, my jumps are a bit drastic because I've given a direct 100 microsecond jump. You can make this finer, maybe even 20 or 30 microsecond, and you'll get much finer turns. But yeah, you can see I'm turning this over here, and this thing moves. So that was, now it's roughly at 1.5 millisecond, which is supposed to be 90 degree. And let's keep going further, and now we're at 2.3 millisecond. Let's go to the maximum, and yeah, this is the maximum. So you can see it, since it started from this point, it has fully reached and completed an arc of 180 degrees. So yeah, now we have 2.5 millisecond on the duty cycle over here. So we can go back to 0 just to show you. So now I'm moving it anti-clockwise, and you can go fast too, there's no problem. So yeah, we brought it to the minimum position. So yeah, this was the digital control, and this is the standard experiment which generally taught in microcontrollers. So now on to the second part, which is going to be, I thought, why not try and implement this in the analog domain, or discrete as we say. So the next one is going to be a discrete circuit. So yeah, now that the digital is done, let's move on to the analog one, and I'll show you the schematic too first. So yeah, now we have the schematic here in multisim, and I'll just break down what it is. So now that we're going to do the discrete implementation of the same servo motor control, what the methodology I have chosen is a cascaded 555 timer config basically. So we have two 555 timers here, and since we know now that the frequency has to be constant, it has to be 50 hertz, but what we have to vary is the duty. So what we can do is we can use one 555 to set up the frequency, a constant 50 hertz astable signal, and second we can use a monostable to vary the pulse width. So with this we can independently change both of them, and even if you change the duty here to the maximum or minimum, this won't get affected. So that's the best part of this. So first of all, the first 555, as I said, is configured as a astable multivibrator, basically a clock or square wave generator. So I have decided these two R1, R2 and C values basically to get 50 hertz. So you can just put it into the calculator, 1.44 by R1 plus 2R2 into C. That's the formula to get 50 hertz. So this will produce a 50 hertz square wave, and after that if we do check out the pulse width of this, it comes out almost to be 90% duty cycle, which is far too much longer than our monostable width. So if you directly feed this to the trigger of the monostable, it's the output is going to be permanently high, because the output of the monostable remains high as long as this part remains pulled low. So we can't directly feed that in here. So basically we just need the pulses, right, like when the rising edge is happening. So for that, what we can use here, you can see, is RC differentiator, and I'll just show you a graph here. What that will do is basically this: when you feed it a square wave, if it's a rising edge, it's just going to give one pulse because suddenly there's a change, and that's exactly what a differentiator does. And at the falling edge, it will give you a negative edge. So, and this is low, at a low frequency. If you see, the graph waveform varies depending on what your frequency is, but since we are doing it at 50 hertz, it's very low frequency, so it's gonna look like this. And since we only want the positive peak, so for that we can just put a diode here, and a small 4148 should do the trick, a small signal diode. So I have decided this RNC basically depending on the the tau equal to RC, which is the time which is required for it to rise. And if we multiply this, it comes out to roughly 100 microsecond, which is shorter. You should choose this value to be shorter than the minimum output of your monostable here, and we know that the minimum output we need is 500 microsecond, so 100 should be good. And another thing is the 558, as I said, it turns on in monostable mode when you pull its trigger low, so it's active low basically. So we do need a inverter here, just a small transistor resistive load inverter here. So we're going to feed that differential signal to this base here through a current limiting resistor, and after that we have a 10k pull up here, and that is going to feed our second 555, which is in monostable, as I said. And this one is going to decide the width. So we need to choose it to be variable between 500 and 2500, same as the microcontroller. And there we had the timer register, here we have a physical R. So to set up the minimum 500 microsecond, I put a 18k there, and to vary the pulse width, the 100k pot, and 22 nanofarad C. So we know the formula of the monostable is 1.1 RC. So yeah, just playing around with that formula, you can, not necessary that you have to use 100k, you can even do 10k, 47k, whatever you want, but accordingly adjust this other R and which is in series with it, and the C. So yeah, we have the output here, and currently you can see I've put a resistive load here, but actually we're going to connect the motor here. This was just for the simulation. So yeah, now that this circuit is clear, and everything is being powered from 5 volts, since the servo is 5 volts, everything is kept at 5 volts. And yeah, just a 10 nanofarads on the control voltage pin. It's a very 103, it's a common thing to put that, it's a thumb rule, just put it. And now we can move on to the hardware. So we have the entire circuit on a breadboard here again. So now that you know the circuit, even though it may seem like a lot of wires, it shouldn't be a problem. So here we have the first 555, that's the A stable one. And here is the small RC differentiator stage. You can see that's the 1 nanofarad and 100k, and that's the diode, the 4148. And there's the inverter. I'll zoom in. So yeah, that's the BC547 resistive load inverter. And over here is the second 555, which decides the pulse width. And this is the pot. I've just inserted it in and added a small knob. And another thing which I forgot to mention is here, since the whole point was making it in discrete, I didn't want to use a power supply. But if you try and use a direct 9 volt battery, and you can use a 7805, that's not a problem. It's what I've done, since we need stable 5 volts. It's a linear regulator. So the problem is that since, as I said, it will suddenly draw, the servo motor will suddenly draw 100 200 milliampere, and 9 volt batteries are preferably for lower current applications, so the voltage will dip suddenly, and that will cause the servo motor to grind and just start buzzing. So a simple fix, what we can do is, you can see here I added this electrolytic giant tank capacitor here. It's 1000 microfarad and 104 in parallel with that. So this is for high frequency noise decoupling, and this is a bypass capacitor, so it'll act like a local energy reservoir, as they say. So since this will be charged up to our 5 volts, I've put it across the 5 volt rail. When the servo suddenly demands current, the electrolytic capacitor will fulfill that, and the voltage will not dip from the battery. So you do need to add this. I didn't add it in the start, and I realized the servo was buzzing, and after adding this, it got fixed. So yeah, you can maybe try 470 microfarad and above, but 1000 microfarad did the trick for me. So yeah, I added that. So now we can just connect this battery here, and I'll show you the waveform again. Same as before, we have 50 hertz again, and now we have roughly 500 microsecond, and the pot currently is in its minimum position. Same, I cannot go any more uh, anti-clockwise, and over there in the digital implementation it was an encoder which had infinite rotation. This has a limit, it's a pot, but it's okay. So now I'll show you the same as before. I'll vary this pot here in the clockwise direction, and you can see that the pulse width will increase. So in the start it's a bit slow, up to 1 millisecond you can see it increase, and now it increases further. So slowly I can increase it for you to see. So now I can show you the, since I showed you the pulse width on the micro oscilloscope, now I can show it to you on the servo. So similarly as I did on the encoder, I'm going to move this pot here, and you can see it's in the minimum position since it's at 500 microsecond. Now I'll just slowly turn it, and yeah, you can see same as before, it's turning, and yeah, we're at roughly 90 degrees now, and same as before it's at around 1.5 millisecond, and let's increase it further. So yeah, now this, yes, this is the maximum position same as before, and here it's at a little higher, 2.75, but that shouldn't be a problem since anyway it's not gonna rotate it once you go beyond its limit. So now we're at 2.5, and you can see it's at the same position. So we can confirm from, like, as the data sheet said, that it can vary between 2.5 2500 and 500 microsecond. So now we can go back to the minimum position here, rotate the pot, and it same as before, it can go fast too. So yeah, we're at the minimum position now, and back to 500 microsecond. So yeah, the whole point of this was to show that not everything has to be in the microcontroller domain. You can always try and do it in discrete, just that you have to have a bit more patience, because you don't, it's not code anymore. You have to manually, wire up the components and decide it. And here in the microcontroller it's much more precise, of course. Here it's a little bit not as precise, and you can feel it changing, but still this teaches you individually. This is sort of like a state machine, if you will, since the first is generating the constant frequency, after that converting it into a small pulse, then using it to trigger the next stage, which is monostable and varying the width. So it's, in that way, it's like a sequential control. So yeah, the whole point of this was to, so demonstrate how the servo rotates based on the PWM which you give it. And we powered everything from a 9 volt, which is nice too. We don't always need a supply. So yeah, I hope you liked this video and learned something about servos. So yeah, thank you.